As with many good things, this started at a SIGGRAPH airport lounge after SIGGRAPH 2 years ago. Vulcanized. So I'm very very happy to announce Jeroen to talk a little bit about the EEVEE viewport in Blender and some of the architecture behind it. So give it up for Jeroen.
Welcome. What a time for engineers to be alive. We're working with the biggest GPUs and with AI that can fill in black spots, perform upscaling, and even generate in-betweens. But I'm not really talking about GPUs as well. I'm trying to find out how we can go to the next slide. But actually, I'm talking about...
Je drukt op de laserknop. Dit is de next slide.
This, okay. But actually, I'm talking about the human brain. It can handle already all the AI features that we have, but it can even imagine full graphics based on just some lines of text. But the last decades, the brain is getting spoiled a bit by all the power that we have on the silicon, on their silicon cousins. The quality of the information that the brain needs to interpret is so high that it doesn't need to do much work. That's all because of the powerful GPUs that are currently on the market, and the smart people who write engines and that produce those incredible images. Hi, my name is Jeroen Bakker. In the 90s, I worked on several demo scenes productions. And actually, I stopped doing that when the GPU became popular, because I was working on CPU rasterization engines, and the GPU took away all my work. But later on, I continued. I came back to the 3D scenes, but I started with Blender, just as a contributor. My first changes were in Blender 2.46, that is in 2008, and I did some work on the node editor and co-developed the tile-based compositor, which has been removed lately. And after that, for Blender 2.8, I worked on the Workbench engine, which is actually the engine that's being used for mainly all the editing and animation parts. Currently, most work on the GPU. Currently, I'm working on GPU-related stuff, and mostly on the Vulkan part. To non-technical people, I always say okay, I make sure that Blender runs on any platform. And for the more technical people, it is my experience isn't specifically render engines, but making sure that render engines perform well on any platform that we support. We're scaling from low-end hardware, tablets, VR glasses, to high-end desktops and workstations. So it is quite a range. The images that you will see, the beautiful images that you will see during the presentation, those are all taken by, created by the OpenMovie Charge. And the rest of the images, those are considered development art. Charge is the 14th open movie from the Blender studio. It is a highly visual, impact, action-packed, 3 minutes long animation inspired by game cinematics and real-time demo formats. The goal of the projects are to challenge Blender and the creative teams to pursue realism and push Blender capabilities in the interactive PBR workflow. Also important to notice that all the content that they were created were handmade. So there's no motion capture involved or facial scans or something else. Everything was hand-drawn. Well, I have a confession to make. My presentation isn't about making those pixel-perfect animations, but it's more related about the technicalities that needs to be done to allow to make such an animation. There's a lot of information sharing online and during the presentations that we saw about creating those render techniques and smart algorithms. But what about the editors and the tools that's needed? Aren't they evenly important? And yeah, this is a graphics programming conference, so programming is in the name. So I will start with a quick start about Blender architecture and move from that towards the editors, the tooling, and then to the final image. Starting with the main loop. This is the actual main loop of Blender. It's in the source code. You can find it out. Even the file is on the top. And Blender will, after it has been initialized, will be stuck in this loop until it gets a signal to be quit. And the actual main loop already points out several interesting points. First point is that the events will be collected from the operating system. Blender can run on many different operating systems, so we have an abstraction layer, which we call Ghost, to collect those events from the operating system. We send them to a queue, so the application can pick that up. These include mouse and keyboards and window resizing events. The application can then handle those events and can trigger changes to the data or operations or whatever the user wants. What's happening then is that areas are being attacked or notified so that they can be updated. And then the areas that have been changed, that will be drawn based on those notifications. This is quite a compressed look at my presentation, and I want to go a bit further and look into this from a data perspective. The core part of our architecture is called DNA RNA. DNA contains the data structures that we use in memory, but it's also the data structures that is stored on disk. It is really old type C structure because it was implemented in the first version of Blender and it still exists. There's a preprocessor that parses the source code and generate a blob containing all the information that's inside the structure. When you save a blend file, the memory is dumped to disk with a least amount of alterations. And at the end of the blend file, the blob of all those structures are stored. So when you read a blend file from a different version of Blender, Blender can detect the structures that were used to save the data and do data migrations. It can also reconstruct your pointers to the new locations in memory that data is stored. So saving a file of a huge amount of data in Blender is really quick. And reading that on the same version of Blender is also quick. When you open it in a new version, it needs to do some processing, but in the end, you will save it again, and it will be quick again. So changing these structures is the only thing that you need to do to access that data, to load that data, to save that data, to migrate that data. There's no other code involved. The second part is from, okay, we have data, but we want to have a better interface for our APIs. With RNA, we can define those, we can define how we access that API for using the things. That is also a compile time. This will also be read during compile time, and it will generate a CPP API and a Python API for you. So only these lines of code. It's really readable and understandable. So almost everyone can do that. Even artists can make changes to this if they want to. So the last part is then, okay, we have an API, then we want to use it. Did you know that you can click on a UI element in Blender and press Edit Source, and then you go to the source editor, and it highlights the line where that button is created. Most of the user interface, the button parts and the control parts, those are just Python scripts. You can actually save it, reload Blender, and your changes will be present. But what happens when you change that file or the element or the data via Python script or via a component? Well, back in the RNA, we also can define some handlers. What happens? What needs to be triggered when the data changes, and those changes, those handlers, those are really tiny. From okay, this material has changed. You need to recalculate the shading, or anyone who's using me, please note I'm changed. Okay, now we did a data-oriented approach, but what does that mean from the user interface? Here's a Blender window. The first thing that you will see is they consist out of multiple editors. And one editor, if you look specific to this one, the 3D viewport, it contains multiple areas. And these areas, they can be tagged when something happens with those with the notifiers. In case when a material changes, the main editor needs to be updated, but the rest of the user interfaces can still use the previous the render of the previous frame. So we don't need to update the buttons. We don't need to. We just copy it from the previous frame. In case you're just moving your cursor around in the viewport and you don't highlight anything, nothing changes, and we even don't do a subchain event. This layer drawing also makes it possible to switch render engines without losing any functionality. So the Workbench engine is a drawing engine that's optimized for modeling, texturing, and animation playback. For animators, it is really important to have a consistent frame rate with a clear layout, so and being able to configure the UI to match the animation speed you want. Cycles, we had a talk about that yesterday. That's our production part tracer. But actually, we only switch the workbench render with the cycles render, and the rest of the user interface is the same. We use a render API where we can hook up other render engines as well. There are multiple dozens of render engines that can work this way inside Blender without touching any Blender code. But we also have EEVEE. EEVEE is our real-time render engine. It doesn't use the render API because it wants to have closer contact with the data structure and that we have in Blender for performance reasons and legacy reasons. The rest of the UI is still the same. We only replace the renderer. And look at the difference that the part tracer does versus what EEVEE can handle. It's not an exact match, but it is really a close match. So do we do everything on the GPU? Many engines are optimized for the highest throughput. And in Blender, it's nothing different, except the definition of a throughput. The throughput for Blender is from, we don't optimize for the highest frame rate, but we optimize for scale, for flexibility, and low latency. But the low latency between the user actually working on the model, performing an action, and seeing the result back on the screen of that action. So that's different than from, okay, let's make something for the highest frame rate. A bit deeper on the topic from the objects that we have in the scene is an object is constructed out of geometry. With the introduction of geometry nodes, the geometry can move between the domains. So a mesh can become a volume or any other geometry type. Making it less clear if something is a mesh, a volume, or a curve. And users are also able to join those different domains into the same object. So basically, you can make an hairy glass marble, and that can still be a single object. For convenience and legacy reason, there's always a primary domain. You add a mesh, then mesh geometry is your primary domain. And that's important for editing, because that determines from if you go to edit mode, that you go to the mesh edit mode. In the next slide, I will explain some of the acceleration structures that we use for the different edit modes that we have. When we edit a mesh, we convert the mesh structure in something that we call the B-mesh. And the B-mesh is an object-oriented like data structure to access mesh data. It allows you to walk around the selection and perform local actions to where you are. Like selecting more geometry around your active selection. It's easy to walk around when you are at the vertex, to walk around every edge that you have and then go to the next vertex. Hey, is this one selected or not? If it is selected, you tag it from, I want to select this one. And then at the end, you apply all the changes from, oh, I wanted to select this one, I'm now going to select it. Another acceleration structure is what we use for sculpting and painting. It's a special data structure that we called paint BVH. And sculpting can be considered an unoptimized retopology yet. It is a BVH structure that quickly detects where a brush hits your mesh. Each leaf in the BVH contains a limited amount of vertices. When the number of those vertices will go over that limit, the leaf will split into multiple leaves. When drawing on the GPU, we only need to upload the leaves that have actually been changed. The other leaves can still use the draw data of the previous frame. When drawing in this example, every mouse movement will update those leaves, except that the debug view that we're using only updates after you finish your stroke. So that's why you don't see it here. Another one is the object mode. In Blender, the mesh geometry is based on n-gons, so not triangles or squares or quads. It can be with any vertex size. Edges and vertices are also separately stored in the data structure. So you can make lines visible without having a triangle. Multiple objects can share the same geometry, but can have a different modifier stack. Like if you have a character and you have duplicated that character, it can have different animations. An animation is part of the modifier stack, and that uses the dependency graph. The dependency graph is still fully executed on the CPU. It's a node-based representation of the scene, including all the relations between the nodes. Specific aspects of your animation can be represented in different nodes to ensure that the updates to other nodes are small, but also to make sure that you don't have circular loops or less occurrence of circular loops. We use an animation anything concept because that's really flexible and creative. And basically what that means is you can have a vertex in your scene, and the location of that one vertex in the scene can alter your render settings, so even your output resolution. So you can hook up any value to anything. And that makes it also really a key case why a lot of stuff is happening on the CPU. Remember this part of the code? DEG stands for dependency graph. And here we tell the dependency graph to mark the shading of the material to be dirty. Nothing more, it's really a tag function. When the renderer kicks in, it will update the dependency graph, and there it will check which node is dirty and recalculate that node. If that node then has dependencies, those dependencies are also tagged as being dirty. And we iterate until that bucket of nodes that are dirty is empty. At that moment, the animation has been updated, but still on the CPU. Do we then do everything on the CPU? That seems like a waste of resources. We don't do everything on the CPU. One thing that we can do is to do a GPU acceleration rated subdivision. We can't do that always. We can only do that when that's the last step of the modifier stack. because otherwise you can have readbacks, and that will intervene with the GPU actions that are still being performed on the GPU. Next to subdivision, another thing that we do is hair. Each strand can have a different number of control points, and basically we can draw those strands as lines, strips, which are 2D view-faced meshes, or 3D cylinders. And we have a global scene setting where we can set the subdivision level for the whole scene. Let's talk about EEVEE. EEVEE stands for Extra Easy Virtual Environment Engine. I don't have time to go over every nitty-gritty detail, and also it's not my experience, but I can go over some of the architectural aspects of the engine and to give a glance how the engine works and how we can get those graphics working on low-end devices. The code base is really readable and quite well documented, pointing out to all the papers and techniques that we have implemented. And that's also easy for new developers to spring on board, because the code just explains how it works. EEVEE is our render engine that provides fast rendering and user feedback by utilizing game engine-like techniques. That's the main goal of EEVEE. The challenge is that the content, what's being rendered, can change continuously, and you don't know what's actually going to change. What is the user going to do? Is it going to change the material, or is it going to subdivide the mesh? And that also means that there's almost no time for baking. So what we do is mostly caching. So we have multiple levels of caching mechanisms to make sure that we can quick update and show the changes to the users. Blender uses different types of GPUs and budgets. We focus our support to any GPU that has been released in the past 7 years, but all the GPUs will most likely also work. We just don't spend too much effort on making sure that it will run with the same performance. And we can scale from low-powered IA GPUs to the latest desktops and workstations. But that also means that we are really conservative on the GPU features that we select. We want to, even if you use a low-powered AI GPU from 10 years ago, the final image should still look the same as when you use the latest GPU. It's just it will take more time to render or display. If a feature isn't available on all the classes of GPUs that we support, we have to implement fallbacks for that feature. So do we do ray tracing? No, we don't. Everything is screen space at this moment. When drawing an object, the geometry, the different geometry types are separated, and we will compile shaders for each material, and each pipeline that is being used by the engine. We have a deferred pipeline, we have a forward pipeline, we have volumes, we have shadows. Those are all different pipelines that's being run. And for each material, for each pipeline, we compile a shader. If the shader, if a material is reused by different objects, then we can sort them automatically inside those pipelines, so that we don't have too much of resource allocations. A material that we can have that can be really complex and really large. And this is just the main tree. There are nodes there that are subtrees that have subtrees that have subtrees. So those are large. The first thing that we check is the topology of those materials. Do we have similar materials with exact the same topologies? In this case, it doesn't matter that much, but if you're only using UBs and shader with some textures with the same texture slots, it helps because you don't have to compile all those different shaders for every pipeline. We, depending on the platform that you have, we can also do some inlining or doing fast linking or full linking. Everything in Blender is written in GLSL. I call it always a Blender GLSL because there are some adaptations that we do, so we're able to not cross-compile, but translate the GLSL to different shading languages, like MSL, or the differences between OpenGL GLSL and Vulkan GLSL. That's all done on top of the using the GLSL as the input. And then we have several levels of cachings to make sure that if we find something in the cache that's already been compiled before, that we can load it and use it and don't need to go to the driver for compilation. Like if you have a slider in your shader and you move from 0 to 1 to 0, if you're back at 0 to, we have already compiled it, so we can reuse it. Oops, next one. Shadows is a really complex topic. Like the scene that I'm using here, it has 6 area lights, and it has quite a lot of details. And how will you be able to run this on an iGPU? Because the image here, that's the image on a laptop iGPU with only 15 watts of power. It just renders that. Not saying it renders it in real time, but it renders it interactive. And one thing how we do that is we have a film pass. After all the pipelines have been rendered, the data are stored in different buffers, but the data, the film pass will read that data and then output it to the correct location in the final image. We also use that to create render passes, which can later on be composite. And we have implemented, in order to be interactive with low-end devices, an upsampling mechanism. And the upsampling mechanism, it allows us to render on a lower resolution and then upscale the samples that have been calculated to a higher resolution without any loss. The quality loss of a lower resolution is fixed by increasing the number of TEA samples. This allows smaller memory footprint and more interactivity without losing quality. And this animation has, the first samples are slowed down a lot, just to make sure that you see the difference and what's happening under the hood. So on low-end devices, there's an option where you can just do one pixel of an 8x8 tile and just let the TEA move to 1,000 samples, and then you get the same image. But then it's interactive. You can get to 15 frames per second, which is fine for an editor. The other way is the other output of the film pass is the different render passes, which eventually will build up to the final image. And the final image, that is something we call the combined pass. And see all the details of what is being rendered. It's all the facial strands and the 3D geometry for the hair, the detailed shadows of the hair on the face. It's all there. So we are now at the end of the journey from Blender's main loop to rendering the final image. And I thank you for all your attention, and I hope that you have a lot of questions for me. Okay, fertig.
All right, any questions? No questions. Thank you, Jeroen. Oh. All the way over there?
Yes.
Can you keep your hand raised? Want to talk?
No, I don't see.
Okay, no questions. Oh, Alex. Hi.
Thanks for the talk. So how do we make ray tracing happen, right? Now we have Vulkan, we have a bunch of IHVs all supporting the same feature set. So yeah, and that's been since 2018, right? So can we leave some really old GPUs behind and just require 2018 and later, and then add ray tracing?
No, we use a lot of screen space effects. If you look at Vulkan, the low-end spec that we have is Vulkan 1.2 with dynamic rendering. And actually everything from GTX 900, 700 series can render that. If you look at the Intel processors, there is a patch will be released of the driver that also the legacy drivers will be able to run Vulkan from that spec. So it is really from, we are pushing the lower limits of the hardware. That is our base, and we build the software based on the lower limits. Yeah.
Hey, so in the Cycles talk, the presenter talked about this virtual machine system to work around the problems that come with having like an explosion of shaders. Do you have something clever that you were doing in? EEVEE for this?
In EEVEE, we haven't done any shader virtual machine. That's really in cycles technology. We are looking into it, so we want to experiment with it. But currently, it is from the node graph, we are generating the GLSL, and we compile that for every pipeline. But compiling is really important for us. So most effort is spent on making sure that the compilation phase is as small as possible. Yeah.
All right. Anybody else? Last question? OK, then I think that's it. Thank you, Jeroen.
Yes.